All right, welcome back. If you recall, that's the code we've looked at last time that basically uses a plain function in order to actually define the heart and soul of a thread. Right? And this function was inc that takes a mutex reference and an integer reference and runs this very tight loop. So clearly the body of the loop is not what's at stake here. What I like to do is see, like, do I really have to separate the definition of a function? And you scratch your head for a second and you say, wait a second. I have this function that I create somewhere else just for the sake of calling it here, of giving it as an argument. I'm giving a function as an argument to a thread. Well, if you're passing a function to something else, that should trigger a fond memory for you. It should trigger the memory of closures, lambdas. Yes, of course, we don't need to define a function for this. We could just get rid of this entire thing and put it directly where it belongs here, in the form of a thread. So let's do that. And let's take a look at version 2 of the code. So inc is gone, and now directly at the mplace backside, I find a piece of code which is a closure. And the closure is right here. It captures two things by reference. Yes, of course, if I define a closure, why would I ask the increment function, or lambda, to take as input the mutex and the value? I might as well, since the mutex and the value are right here, directly capture them by reference so that they are again shared, but they will be in the state of the lambda, in the state of the closure, and I'll be able to access them just exactly as usual. So I'm using closures to get rid of this stdref that we had before, right? Remember here, I had to actually use stdref to package a reference to m, and stdf to package a reference to val, and then the function had to be stated separately. All of this is gone. Now I capture m and val by reference, and I directly put the body of the function here, which, as you expect, is still doing a for loop, is still simply locking, increasing, and unlocking. So the logic hasn't changed, but now the code is tidier in a sense. Everything is put together. So great. This gives me a more readable code, and the main advantage is no more stdref, and the body of the thread is visible exactly at the place where I create the thread. So lexically speaking, if I look at this piece of code, I see everything. I don't have to move around in the file and go find the inc function to understand what it does. Everything is in place, directly accessible at my fingertips. And that's the beauty of it. So let's see whether this works better than what we did before, right? So let's go in, and now this time I'm going to load thread 1. And thread 1 is what you expect. I still have my mutex and value, but in the loop now, notice here how the two arguments for my threads are now captured by references. And now I have my closure definition. So the closure basically does my loop, and that's what you see here. The loop goes a million times, locks, increment, unlocks, right? Same story. And at the end, nothing has changed. I still need to join and do all that good jazz. Great. So let's go in the shell and let's compile now thread 1. So I'm going to go reuse the command, change to thread 1, change to thread 1. Sanity check, I'm running parallel code. Always run with one thread first. Okay, that seems to run fast. Time. Look at that, since 0.03, that's perfect. Now the moment of truth. Has this change had any impact on performance? No. This hasn't fixed performance. 5.3, well, maybe a little bit, but really nothing really significant, right? This doesn't change the bottom line. I have code that's more readable, so I've made progress in terms of readability, but I haven't quite made progress in terms of performance. This is easier to read, easier to communicate, but certainly not faster. Okay, that was the first take. Now, can I go any further on this? Well, in terms of readability, we could still do something a little better, right? Look at this. The body of the for loop always has the same structure. It is a critical section. So I'm going to lock the mutex, do what's critical, unlock the mutex, right? It's always the same. Lock, do, unlock. And then we're out of the block. That's always what I want to do. And my point is, well, if that's always what you want to do, that's kind of silly. Because it's very easy to forget that line and write this instead. If you do that, you can slip. Because you have a lock, you have a do, you don't have an unlock. So the next time you loop around, it's going to deadlock and you're going to have silly bugs. There is nothing to guarantee that you call unlock. You cannot make sure you're doing it. If you're in a critical section, I like to remember that I always have to unlock, right? That's my main point. I like to make sure that the unlock happens. So there is a solution to that, and it's to use something slightly different. Remember that objects that are created on the stack, if I create an object X here, then this object gets created when I enter, and when I leave the block, the destructor of this guy, tilde X, gets invoked automatically. Okay, that's cool. So what if I had an object whose constructor calls lock and its destructor calls unlock? Then the lock call disappear, the unlock call disappear, I just put the declaration of my blue locker, and that's all I gotta do. When I enter, the blue locker is going to lock. When I leave, the blue locker is going to unlock. In the meantime, I will simply do my loop here. So the code gets simplified. Now, all I have to actually realize is this tiny little thing. I'm going to say, okay, let's call that a guard. I'm going to have a guard. Let's call him X. And then I'm going to do, and then that's it. Because when we enter, the guard is going to lock, then I do, then on exit, the guard is going to unlock because its destructor is called. And that will happen at each iteration of the loop, right? So this works well. So, but what does the guard lock? Well, yeah, he still needs the mutex. So in reality, we got to pass the mutex here, right? It's a minimum. He has to have the mutex. But otherwise, that's going to allow us, relieve us from having to remember the importance of this unlock and the fact that it needs to be paired with the lock. And what I just discussed for you is the next implementation, which is called a guarded implementation. And what you see here is that the STL provides a type called lock guard. It's parameterized by the type of lock you use, because there are several different kinds of locks. So here the lock guard is using a mutex. It's using mutex M, it's telling you in the constructor which one, and then of course it just does the work of incrementing val by 1. I don't have to lock explicitly, I don't have to unlock explicitly. All of this is taken care of by the guard. By putting a guard in front of the block, I'm making sure that the entire block is a critical section. The whole thing. The whole block is a critical section, and I'm fully supported. That makes the code even shorter. No more lock, no more unlock. It's beautiful. I just have a guard. So let's see how well that does, right? And as you might expect, I have a file for this called, hopefully, thread 2. And here we are. We are in thread 2. And look at this. Inside my for loop, the first line of the body is creating a lock guard parameterized by the mutex type. My guard is called G, is going to actually use M to do the locking and the unlocking, and then I can write my critical section. And that's it. No need to lock and unlock explicitly. It's the guard's job to do it, and it's guaranteed to always happen, because when I leave the block through the curly braces, this gets taken care of. So that's the beauty of this approach. Now again, rise the question, have we improved performance? So let's take a look at this. Now this is thread 2. I go back in my shell. I'm taking thread 2, compile this, run thread 2. So once again, we'll do one thread. Okay, that seems to go fast. Great. Now let's run with 2. And once again, we shrug, right? This is not good. My code is more readable, so my colleagues are certainly going to be happy because I'm making their life easier, but performance is still an issue. So this is the problem that's really plaguing us since the beginning of this sequence, and we have to try and make an improvement and understand what's really going on. That's what we're going to do next time.